Thanks for taking a break with us. I'm Mark. This is Arnon. During today's break, we'll be discussing open APIs and why DSPs are so good at math. But let's start with a discussion on DSP application spaces. For customers not familiar with DSPs, one of the most common questions is, are DSPs a good fit for my application? So I ask you, Arnon, which end equipments do DSPs play in?
Oh, well, we spent a lot of time talking about low power and embedded, but let me talk about a different aspect of DSPs. So one aspect the DSPs are good at is streaming data coming in, having to do something with that data in a real time and provide an answer out. So what kind of applications are good for that? So we've talked about machine vision, so you've got data coming in. We've talked about communication signals, so you've got, again, data coming in, you need to react. You've got audio, same thing, video processing, medical equipment, so portable ultrasound, you want to see the image on the screen as you're doing it. So anything where you have streaming data coming in, you have to act to it in a real time, and there's some constraint on the environment.
Okay, so a lot of different applications is what I'm hearing.
A lot of applications fit that
I can't
space.
come up with as many off the top of my head as you do, so I actually did some preparation. I went to our DSP database and I printed out a list of all the different end equipments that DSPs have been designed in the last 2 years that we sold products.
How many?
233 came up.
Wow.
All the way from, in alphabetical order, the C5509 in access control and security to the 6678 8-core DSP in X-rays for medical and surgery. So a lot of different things. It seems like DSPs play in just about every area. So I think when customers say, do DSPs a good fit, chances are they are.
Yeah, and again, looking for streaming data, looking for a constrained environment, 200
currency counters,
places to play,
landmine detectors,
yeah,
net video recorders,
nice,
software-defined radios. I'm out of pages.
All right. So there have been several open APIs like OpenCL and OpenMP gaining traction in the market. How do these open APIs work with DSPs, Mark?
Well, they actually work very well with DSPs. And you mentioned OpenMP, OpenCL. These are ones that are freely available inside our multi-core software development kit. So they're really good things to help people program multi-core systems, to make multi-core devices less complicated, right?
Yeah, so, what the market has found with the open APIs have come from are people going from single-core devices to multi-core. Whether it's TI, whether it's somebody else, a lot of us learn to program in a serial way. Right? Program as if there's one thread running, there's only one core. So now what happens when you're given a device that has multiple processing elements?
What do I do?
Yeah. So, OpenCL is one, OpenMP is another one.
Yeah, and I guess OpenCL is good for the heterogeneous case where you have two different types of processors. In our case, it would be ARMs and DSPs, yeah. And so you can have the ARM dispatch task through OpenCL to the DSP, use that kind of as an accelerator. And then OpenMP is more like the homogeneous core, so when you have similar cores, all the same. So like our 6678, which I just mentioned in the X-ray, right? You have 8 of those cores, and the OpenMP allows you it will parallelize the task for you.
And it's
using
really good for scaling.
Elements, yeah.
So you can take a 1-core solution and easily go to 2, 4, or 8, just like in those DSPs.
Yeah, absolutely. All right. Well, I've got a simple one for you. For several videos, we've been repeating that DSPs are great at math, but really every processor can do math. So I ask you, Arnon, what makes a DSP so good at math, and how is this different from other processors?
And this is simple?
It's simple because it's going to you.
All right. Well, DSPs are good at math for a couple of reasons. So number one, you have to have math operations or arithmetic units available. Right? Mm-hmm. So we have a lot of parallel processing elements in the DSP to do the math. But you also have to get the data to the processor, which is equally important. And then the third one is having instructions that you can build on, sort of simple instructions to build complicated functions. And so we have all of those. And so the data movement is the EDMA. It's called Enhanced DMA data movement.
And I think that's key because it's really, not only do we have a great engine with how many multipliers we have, but you got to keep that engine fed. And so the Enhanced DMA is great for that. And I know it works in very complicated. It has like 2D and 3D access patterns to get into the memory.
Yeah, so a typical processor would have cache. So if I'm grabbing, from space 1, it'll automatically grab from the next thing that's in line. Yeah. But if you have a complicated system that might be grabbing data from different places, and you want to move that data in at the same time that you're processing, typical cache systems won't do that. So having a DMA is a big deal. And then the instruction set, having an instruction that's optimized for complex math, having an instruction that actually can reorder data within a 64-bit window is actually really effective in things like machine vision, believe it or not.
Yeah, I do believe it. And I think it's pretty amazing that, like our latest 66X core, they had it like 90 new instructions, right, for complicated like vector and math operations. And so like our old code, it's still backwards compatible. It'll still run the old code, but you added these new instructions that can give it even more performance and better lift if you take advantage of it.
Yeah, so it's really a combination of a few things that allow us to do that.
But see, simple.
Yeah, very simple. You got all that? All right, let's move to the wrap-up.
Let's do it.
All right, summertime still, so baseball. I know you like baseball. I know you're kind of a hoity-toity upscale guy, so I'm sure you're excited that they have sushi. So what's your favorite thing to eat at baseball parks?
All right, so clearly that was sarcasm for those who aren't aware, right? Sushi, I don't eat it outside of ballparks. I'm not going to eat it inside a ballpark. You're not taking away from the traditional hot dogs, although I've gone to one game this year and had cheesesteaks.
Oh, that's good.
So you eat the sushi?
Not at ballparks.
Okay. All right, we talked earlier about DSP and their end equipments. What's your favorite DSP end equipment and why?
I have to say communications equipment. I spent 20 years, researching and working on comms equipment, so I'm still kind of a soft spot for phones and base stations and all that kind of stuff.
It sounds like a long 20 years and a waste of a PhD. But I actually prefer the audio, the audio space. We had an audio software team that was right in the beginning of the portable players. We had the first MP3 AAC player on our TI DSP. So that's my favorite, is the audio.
Yeah.
With medical close behind.
To get you back there, I know you're a big Tom Brady fan,
Yes,
so what
I
can
am.
you tell us about Deflategate and the rampant cheating that goes on in the New England Patriots?
Okay, we're out of time now, so thanks for taking a break with us. Tweet us your questions and comments using the hashtag DSPBreak, and we'll address them in future videos.
And don't forget to follow us on Twitter. Check out ti.com/DreamDSP for all the latest info and material on TI DSPs. And to help you remember DSP, think Deflated Super Bowl Patriots.